Have you ever cracked open an electronic device and just stared, wondering how it all actually works? Well, today we're pulling back the curtain on the fundamental rulebook that governs literally everything with a circuit. We're talking about Kirchhoff's laws.
And that's the big question, isn't it? You look at a circuit board, and it's like this impossibly complex city of tiny components. How on earth do you even begin to figure out what's going on in there? It honestly feels like magic, but I promise you, it's not.
And the person we have to thank for that is this guy right here, German physicist Gustav Kirchhoff. All the way back in 1845, he came up with two, brilliantly simple laws that let us understand and build even the most complicated circuits. He basically gave us the map to navigate that tiny city.
Okay, so let's jump into his first rule, the voltage law, or KVL for short. Now, the big idea here is something you've definitely heard of before, the conservation of energy. The easiest way to think about it is like a budget. The battery gives you a certain amount of voltage, and by the end of the trip, you have to spend it all.
So here's the official textbook definition. It says that in any complete path, or loop, the voltage you gain from the power source has to equal the total voltage you lose, or that gets dropped, across all the other components in that same loop.
To put it really simply, what the battery gives, the circuit has to use. There's no leftover voltage. If your battery supplies, say, 9 volts, then by the time that current makes a full lap all the way back to the battery, every single one of those 9 volts has been used up. The books have to balance out to 0.
Now here's where it gets cool. This one simple rule behaves differently depending on the circuit layout. In a series circuit, where everything's in one single line, the components have to share the voltage. So if that 9-volt battery is powering 3 identical lamps, each one gets a 3-volt piece of the pie. But in a parallel circuit, each component gets its own private loop back to the source. And that means each one gets the full budget, the entire 9 volts all to itself.
All right, that was energy. Let's switch gears to Kirchhoff's second rule, the current law, or KCL. This one isn't about the energy budget, it's all about the actual flow of the electrons themselves. And it's based on another pillar of physics, the conservation of charge.
And the formal rule is just as straightforward. It says that whatever amount of current flows into a junction, a point where the wires split, the exact same total amount of current has to flow out. It's that simple. Electricity can't just disappear at an intersection.
The best analogy is traffic at an intersection, right? If 100 cars drive into an intersection, some might turn left and some might go straight, but you're still going to have a total of 100 cars leaving that intersection. Current behaves the exact same way when a path splits. So how does this look in our circuits? Well, in a series circuit, it's just a one-way street. There are no junctions, no splits, so the current is exactly the same at every single point. But in a parallel circuit, the path does split, so the total current coming from the battery gets divided up among the different branches, and then it all adds back together when the paths merge again.
Okay, the theory is great and all, but let's see how these two laws work together to solve a real problem. We're going to dive into what's called a mixed circuit, one that has both series and parallel parts all mixed together.
So here's our puzzle. We've got a 40-volt source. We can see that the voltage dropped across lamp 1 is 10 volts, and the voltage across lamp 3 is 20 volts. Our mission, should we choose to accept it, is to figure out everything else.
And we don't need to guess. There's a method to the madness. First, we're going to trace all the voltage paths using KVL. Once that's done, we'll look at the current at the junctions using KCL. Simple as that.
Okay, let's start with voltage. The first thing you should spot is that lamps 3 and 4 are in parallel. And what's the rule for voltage in parallel? It has to be the same for both. So if V3 is 20 volts, then V4 is also 20 volts. See? One down already. Now, what about V2? We just trace a full loop. The source voltage, 40, has to equal the drop at lamp 1 plus the drop at lamp 2 plus the drop across that whole parallel section. So our equation is 40 volts equals 10 volts plus V2 plus 20 volts.
Wait, I said V2 was 20 volts? No, V3 and V4 are 20 volts. My mistake. The equation is 40 equals 10 plus V2 plus 20. So V2 has to be 10 volts. Much better. We used the rules and solved for every voltage. V1 is 10, V2 is 10, and both V3 and V4 in parallel are 20 volts. It all checks out. Fantastic. Voltages are done. Now let's tackle the current using KCL. So let's say the total current leaving the battery is 0.40 amps. It flows through lamps 1 and 2, no problem, and then it hits that junction where the path splits. We're told that 0.10 amps goes down the path with lamp 3. So
where does the rest of it go? Well, it has to go through lamp 4, right? KCL tells us what goes in must come out. If 0.40 amps go in and 0.10 amps go one way, then the remaining 0.30 amps have to go the other way. And just like that, puzzle solved!
So, we've walked through the theory and put it into practice. Let's just boil this all down one more time to the absolute key things you need to remember.
Honestly, this right here is your cheat sheet. This is everything. For series circuits, just remember, voltage adds up, current stays the same. For parallel circuits, it's the total opposite. Voltage stays the same and current adds up. If you can remember this table, you've got the heart of circuit analysis down. And really, that's it. 2 beautifully simple, elegant laws that are the absolute foundation for every single electronic device we use. They aren't just some abstract concept from a physics class. They're the tools engineers use every day to literally design our future. So now that you get it, the only real question left is, what are you going to build?